Alright, welcome everybody to this week's edition of Physics Fridays. I am your host, Eli Hibbett, and so we are reading the Elegant Universe, at least I am, and this week I read Chapter 2, and so what it's about is, last time when we left off, we were talking about the different types of matter. We have, first we thought that, molecules were atoms, and then atoms were atoms, and then protons and neutrons and electrons were atoms, and not the case. Here we go down to electrons, quarks, and neutrinos, and now we're positing that not even this is the case, that there is something under that known as strings. But Chapter 2 doesn't have anything to do, we don't talk about strings really at all. But he does sort of allude to the fact that in order to understand this, you got to understand general relativity first. And I see where he's coming from now that I read the chapter. And so he gives, a couple of classic little, paradox examples to kind of illustrate relativity. And I guess for me, the best way for me to understand relativity is to think about driving a car. When you're driving a car, I'm not moving, in some sense. I'm sitting in a car. I'm not doing anything. But when you're standing on the side of the road, you are definitely, to that guy standing on the side of the road, you are jamming. You're going 60 mph. And that's relativity, man. I mean, that's it. To one person, you look like you're moving, and to me, I look like from my perspective, I'm sitting still. And the other, I guess, interesting thing with cars is, if I'm driving 60 miles an hour and someone is driving towards me at 60 miles an hour, it's the same as if they were stationary and I was driving 120 if we collided, or, for whatever, or just even driving past each other. We're making measurements while we're passing each other. That sort of thing. And so if I'm driving 60, let's say I'm driving 120 on the road, right? I'm just going nuts. And everyone else is going 60. For me to maneuver around these people, it's like having stationary objects and I'm going 60 miles an hour. You sort of see how, that's relativity. My relative speed to them, my speed relative to them is 60 miles an hour. And so you're navigating around stationary objects going 60 mph, which is why you should never go that fast. But it's kind of an interesting, analogy for relativity. So we get a couple of those. But the first thing that he talks about is, of course, Einstein, who introduced the theory formally. And the first thing is that we have light, and light propagates through a medium at light speed, 3 times 10 to the 8th meters per second. We know that, and we know that nothing can travel faster than light. And the other thing that is very interesting, so if I'm driving my car, right, and I take my foot off the gas, I am going to coast to a stop. And so there is this, sort of friction, that causes you to stop. But not the case with photons. Photons just go the speed of light all the time. And it's not entirely true, because, depending on the medium, there is a speed limit. But they are going that speed, and that's it. Nothing is stopping them, which is a very interesting, property of light. But the other thing is that we know it's an electromagnetic wave, and it has two components. It has an electric wave, sinusoid, and then it has a very much smaller magnetic sinusoid, and they go perpendicular to each other. So you got the magnetic one going this way, very small, and the electric one going that way, much larger. And that is a photon. Now they do exhibit, particle-like, got the wave-particle duality of everything, but let's forget about that for now. Let's get into the relativity of it all. So we get the George and Gracie classic example. George and Gracie are astronauts sitting in space, in the middle of space, in the middle of nowhere, gazillions of miles away from the nearest galaxy. And let's just hop inside George's spacesuit for a second. And he's hanging out, and in the distance he sees Gracie. Well, first he sees just a little strobing light, and then he says, "Oh, okay, that is Gracie," and whoosh, off she goes. And so he says, "Okay, she moved past me." Next thing, let's get into Gracie's spacesuit for a second. And same idea. She's sitting in the middle of nowhere. They're both wearing, this flashing thing. So now she sees flashing light. Mr. George goes past. And from her perspective, she's not, she's stationary and he moved past her. So who moved is the question. Now, if you're traveling at constant velocity, the idea that you're in the middle of space is the idea that you have no point of reference. And so you cannot tell who is moving with respect to something. And if they're moving at constant velocity, there's no acceleration, you don't get that feeling. You can't tell that you're in motion once you are at a constant velocity. So, depending on whose reference frame you're in, this is the big thing, depending on the reference frame, depends on who's moving, so it all is all based on what you consider stationary, what you consider, your point of reference, which is the whole idea behind relativity. Now, the other thing, we get another classic example of two world leaders in a moving train, and instead of sitting, the train's going this way, they're sitting like this. One's sitting facing the back of the train, one's sitting facing the front of the train, and they want to sign this document at the exact same time. So they turn the light off, and when they turn the light on, they're both going to sign it. So neither one, will be considered, having given in. And once they turn the light on, they say, "Hey, Mr. guy facing the front of the train actually signed it first because the light reached him first, because he's there, the train's moving, the light comes and hits him first, while the guy kind of running away with the train, the light hits him second." And sort of, valid measurements. And if you are in the train, you see no difference. So, question mark. But the idea is, it's all relative. It's all relative. And you will actually, depending on your reference frame, you will actually measure different things. And so, here we go with time dilation and length contraction. So, if you are, if I'm going 10 miles an hour, I do somewhat, to the stationary observer contract, but for our speeds, relative speeds, it's never gonna matter. You're not gonna see anything. But if you're going 90% of the speed of light, 95% of the speed of light, 99.999% of the speed of light, it really, you get shorter. And if you go slower, you get longer. So, depending on whose reference frame you're in. And same thing with time. When you're moving, time moves slower. And when you're stationary, time moves faster. And so, we didn't deal with the twin paradox or anything like that. We don't get into the, these do not jibe paradoxes. Like, what happens if you're going the speed of light, or let's say 99.999% of the speed of light, and then you just fit into a barn, and as soon as you get into the barn, you hit the brakes, and, they slam the door. What happens? Do you bust out the end of the barn, or, how does that happen? We don't worry about those sorts of things here. We're not trying to confuse anybody. We're trying to illuminate everybody. So, we talked about that, and the one thing that he does mention that's very interesting is that in all reference frames, the speed of light is the speed of light. It's not, you can't slow it down by traveling, the other way or anything like that. So this is a very important thing. But so the other piece of the puzzle that, and when I was reading this, I was getting kind of bored, I guess you'd say. I was like, I don't really see where he's going with this, and I actually knew the information, but it just didn't click with me. So there's this dude, and he's driving 100 mph, right? And so he's supposed to drive straight down this track. So the track is 10 miles long. Should take him 10 minutes, right? Or whatever it is. Doesn't matter. Not important. Well, you drive down the track, you're driving at some speed, let's say it takes 10 minutes. And he drives, 3 times perfectly, 10 minutes, no problem. And when he goes into the next couple of measurements, it's starting to take him a little bit longer. And no one can figure out why it is. He thinks maybe, something's messed up with the car, yada, yada, yada. But what happens is, I guess, for the sun kind of hits him in the eye and he starts going at a little bit of an angle. He's not going straight down the track. So as he's going more and more of an angle to, for whatever reason, I guess, not, get sunlight in his eyes, he's actually traveling a longer distance because, he's starting to travel at kind of like a triangle now, the hypotenuse of a triangle. If you've been listening to the Pony Your Homework Physics Series podcast, this is right up your alley. And so we all know that the hypotenuse of a triangle is longer than the leg. And so, he's giving some distance to this other dimension. He's not traveling down, a single dimension now. He's going two-dimensionally, and so it's taking him more time. And so the contention is that this is what's happening with light. When light starts to manifest itself or travel in spatial dimensions, it slows down and becomes matter. And when it's only rolling through time, there is no time for light. Time does not move. It's just, light is just rolling along in the time dimension, and that's it. And this is where E equals mc squared comes from, that you can go back and forth between energy and mass, and then when you convert all your mass to energy, you become light, or some sort of radiation, and you're not going to be able to go faster than light. And in order to go faster than light, you would need an infinite amount of energy. So nobody's breaking the cosmic barrier. Now, something that I had come across when I was in college was this notion of, so the speed of light is the cosmic speed limit on both sides, I guess you could say. If you are going slower than light, you cannot go faster than light. You can never achieve faster than light. But there are these proposed things, particles that are traveling faster than light, and they cannot slow down. They cannot go slower than, at no point can you ever go slower than light. And the cool thing about this is that if you're going faster than light, you're going backwards in time. So kind of reverses the direction, and this is all kind of, nobody really, or at least I haven't read anything about, experimental verification of this yet. But I think I'm going to kind of dig into that, because it's a very cool idea. So if you're going slower than light, you can't go faster, and reverse, But the one last thing I wanted to touch on in this chapter that I thought was sort of interesting was the idea of muons. Muons have a very, very short lifespan when they're stationary, but if you accelerate them in a particle collider, not only do they gain mass, but their
lifetime before they spontaneously decay is much longer. And depending on how fast you move them, it can be, 7 times longer. And I believe he said something like 200 times longer as you start, really moving them around. And it's because time exists slower for these particles when they're going that fast. And they kind of talk about, the wristwatch of the muon, like it's just waiting to decay, and it's, no, that's not, I have, my wristwatch is running a little slow today, kind of thing. But, so those are kind of the highlights of this chapter, and of relativity in general. But, yeah, so I actually started digging into a little bit of chapter 3, and apparently we're going towards gravitation, and we are going to merge gravitation and relativity. So we'll see what happens. I read like 2 pages. I didn't really dig that much into it. But yeah, so that'll be next week, chapter 3. It's called Of Warps and Ripples. And just in case, just to titillate you, this is a copy of my Elegant Universe, which I've been reading, using the magic card as a bookmarker. So with that, I hope you're digging it, reading along, and getting a little extra out of this. So I will see you next week, and I bid you adieu. Take care, guys. See you later.